A cheap kitchen knife loses its edge after a few weeks of ordinary use, and a good one needs sharpening every few months, because there is a basic trade-off in steel: make it hard enough to hold an edge, and it usually becomes brittle enough to chip or snap under stress. Now picture a blade forged over 1,000 years ago that was supposedly hard enough to hold a razor edge indefinitely, flexible enough to bend almost double without breaking, and sharp enough, according to persistent medieval legend, to slice a silk scarf that simply drifted down onto it. Modern metallurgists cannot fully explain how it was made, and for more than 2 centuries, nobody on Earth has been able to reproduce the original material. That is not folklore dressed up as science. It is roughly the real story of Damascus steel, and the material science behind it was strange enough that a team of German physicists needed an electron microscope and a vat of hydrochloric acid in the 21st century just to figure out part of what was actually happening inside it. The steel itself did not originate in Damascus at all. It began as an ingot called wootz, a word derived from ukku, a term for steel used across parts of southern India, produced in dedicated furnaces in India and Sri Lanka, with some of the oldest surviving furnace sites dating back roughly to the 5th century BCE. Indian metalworkers had been refining the crucible process for well over 1,000 years by the time merchants began carrying finished wootz ingots west along trade routes into the Middle East, where smiths in cities like Damascus forged them into the blades that would eventually carry the city's name, even though the raw material and the core smelting technique both originated somewhere else entirely. The process itself was a genuine feat of controlled chemistry performed without any of the instruments a modern chemist would consider basic equipment. Iron ore, along with specific plant material and wood, was sealed inside a small clay crucible and heated to extreme temperatures, allowing the iron to absorb carbon from the burning organic matter until the resulting steel reached an unusually high carbon content, typically somewhere in the range of 1.5%, several times higher than the steel used in most swords of the period. Ordinarily, that much carbon makes steel dangerously brittle. Wootz steel cooled slowly and carefully inside the sealed crucible over a period of days, instead formed a distinctive internal structure, bands of hard iron carbide particles arranged in wavy, layered patterns running through a softer iron matrix, which is what produced the rippling, almost liquid-looking surface pattern that became the blade's signature appearance once it was forged, ground, and etched. That microstructure is also the reason wootz-derived Damascus steel is fundamentally different from the material most people today would call by the same name. Modern pattern-welded steel, popularized commercially in the 1970s, achieves a similar rippling visual effect by folding and stacking separate bars of two different alloys and hammer welding them together, creating a mechanical sandwich of visible layers. True historical Damascus steel involved no folding or layering of separate metals at all. The pattern emerged naturally from a single uniform ingot as it cooled, driven by microscopic crystal growth rather than macroscopic construction, which is part of why genuine wootz blades are considerably harder to reproduce than their modern folded imitations. By the middle of the 18th century, the original wootz production tradition had effectively disappeared. The exact combination of trace elements present in specific Indian ore deposits, the precise composition of the crucible clay, the particular plant material used as a carbon source, and the multi-day cooling schedule that allowed the carbide bands to form correctly were never fully documented as a single transmissible process, and as trade routes shifted, ore sources changed, and European steelmaking industrialized around newer methods like the Bessemer process, the specific conditions that had produced true wootz simply stopped being reproduced, and the knowledge faded with the smiths who had carried it. For roughly 250 years afterward, the recipe was effectively gone, leaving behind only surviving blades, admiring written descriptions from travelers and soldiers who had encountered them, and a great deal of speculation about what exactly had made the material special. In 2006, a physicist named Peter Paufler at the Technical University of Dresden led a study published in the journal Nature that examined a fragment of a genuine 17th century Damascus sabre using high-resolution transmission electron microscopy. To get a clear look at the steel's internal structure, Paufler's team dissolved a sample in hydrochloric acid to strip away the surrounding iron, and what remained, preserved inside the material, were carbon nanotubes and cementite nanowires encased within them, a nanoscale structure nobody had expected to find in an object forged centuries before anyone knew atoms existed, let alone had a name for a nanotube. Paufler's team proposed that trace impurities naturally present in the Indian ore, Elements like vanadium, chromium, and molybdenum in very small concentrations may have acted as a catalyst during the slow heating and cooling process, encouraging carbon from the crucible's plant material to form these nanotube structures, which in turn may have helped organize the very carbide bands responsible for the blade's rippling surface pattern in the first place. It is a mechanism nobody involved in the original process could have understood or intentionally engineered, since the concept of a carbon nanotube would not exist in scientific literature until the 1990s, roughly 200 years after wootz production had already died out. None of this fully closes the case. Despite decades of dedicated metallurgical research since Paufler's paper, modern scientists still have not managed to reliably reproduce a blade with the same verified performance and microstructure as the finest surviving historical examples, because reconstructing the process means matching variables that were never precisely recorded in the first place. The exact trace element profile of ore that came from mines depleted or lost centuries ago, the specific plant species used for the carbon source, and a cooling protocol that was passed down as craft experience rather than written specification. That gap between admiring a finished object and being able to reliably recreate it is in some ways the whole story. Historical accounts from the Crusades describe European soldiers encountering blades that could reportedly cut through mail armor or slice a piece of silk that had simply floated down onto the edge. And while some of those specific stories carry the exaggeration you would expect from centuries of retelling, the underlying material really was measurably different from contemporary European steel, hard enough to take an exceptionally fine edge while somehow avoiding the brittleness that high carbon steel should have produced. What makes the story genuinely unusual, rather than just a case of ancient craftsmen being skilled, is that the finished blades appear to have worked because of a nanoscale structure their makers had no way of observing, verifying, or intentionally controlling in the way a modern materials engineer would. The Indian metalworkers who perfected wootz steel were, by every available account, extraordinarily skilled empirical craftsmen, refining their process through generations of careful trial, observation, and inherited technique. What they were not doing, because the tools did not exist yet, was looking at their own steel on a nanometer scale and confirming why it worked. They simply knew, through results repeated often enough to trust, that this particular combination of ore, fuel, crucible, and patience produced a blade unlike any other available at the time. Modern bladesmiths today can produce steel that performs exceptionally well, in many cases outperforming historical wootz on standardized modern metallurgical tests, using alloys engineered with a precision no ancient furnace could match. But that is a different achievement from reverse engineering the original process itself, and reproducing a blade that is, atom for atom, structurally identical to a 17th century wootz sabre remains, as of the most recent published research, still out of reach. The next time an ordinary kitchen knife needs sharpening after a few weeks of normal use, it is worth remembering that somewhere in southern India, more than 2,000 years ago, someone sealed iron and leaves inside a clay pot, buried it in a bed of coals, and, without any concept of chemistry, as we understand it today, produced a material laced with structures on a scale smaller than light itself, structures modern science only learned to see for the first time in 2006.